Hey there, Math Hoppers. In this video lesson, we are going to learn about functions and their graphs. And because this is for our pre-calculus course, we will go through domain, range, intercepts, symmetry, and odd and even functions. So let's remember that the domain is the set of all x values for a function. And looking at this graph of this function f, let's start with the closed circle, the point -3, -2 when we look at the domain. So the closed circle at -3, -2 tells us that the x values start at and include -3. Notice the graph does not exist to the left of -3. That tells us the lowest point in our domain is -3. Moving to this open circle at 0, 2. The open circle tells us that 0 is not in the domain. And why is that? Because if we were to put 0 into this function, we would not return a value. That's what the open circle means. So 0 is not in the domain of this function. It is clear the intended height of the function is up here at y equals 2, but 0 does not exist because there is no return value for 0. Now the arrowhead on the right-hand side arrowhead tells us that the graph continues without bound, actually for both x and y values. But just looking at the x values, or the domain, this would continue to get wider and wider and wider and include all x values through infinity. So the domain of this function is from -3 inclusive to 0, where 0 is not included, and then it jumps, this little union symbol says it jumps from 0, again not included, to infinity. So basically all real numbers past 0, not including 0. All right, so when you see these two soft brackets, remember that means something's not included. So this tells us that the domain starts at -3, it skips the value of 0 and goes to infinity. The reason infinity has a soft bracket, infinity is not actually a value, so we cannot say that it is included. Determining the range. Recall that the range is a set of all y values for a function. We are going to take the same exact function we just looked at, and we are going to look at the range. So starting with that point at -3, -2, when we're looking at the range, -3, -2 tells us this is the lowest output for this function. The graph does not go below -2. So the lowest value for our range will be -2. Let's go look at that open circle. The open circle at 0, 2 does not affect the range. The fact that there is a hole here proves that the intended height of the function is y equals 2. So 2 is included in the range. So I know this is a tough point for people to get, but these holes in the graph affect the domain. They do not affect the range. The fact that this exists and there is this hole here tells you the intended height of the function is 2 when x is 0. Looking at the arrowhead on the right, we've already talked about this, but let's talk about it again. The arrowhead on the right-hand side tells us the graph continues without bound, so it will include all outputs for y, continuing on to infinity. So our range is simply -2 inclusive to infinity. Remember, soft bracket on infinity. Let's really quickly look at the y-intercepts. These haven't changed much since we first learned about them in 8th grade. The y-intercept of a graph is the point where the graph crosses the y-axis. Looking at this graph of f of x, we see that it crosses the y-axis at 0, 1, right over here. So our y-intercept is 1. Now, remember, we also can find our y-intercepts algebraically. In fact, it's often important to do so if you have to estimate. We're not going to do that here since it's something we've been doing since the 8th grade. But remember, the y-intercept is the point where the graph crosses the y-axis. So you haven't gone left, you haven't gone right. Because you haven't gone off the y-axis, x is 0. So to solve algebraically, if you're given the function, you would put 0 in for x and solve for y. But in this video, we're just focusing on graphical y-intercepts. Let's look at something that you would probably want to do algebraically though. So given the function of g of x, I can estimate the y-axis. It appears to cross the y-axis at 0, 4.7. It might be 4.6, it might be 4.65. I can only estimate it. So since it appears to cross at 0, 4.7, the y-axis, the y-intercept is approximately 4.7. Now, we will take a longer look at x-intercepts, or the zeros of our function, because they are used extensively in pre-calculus. Remember that the x-intercept of a graph is the point where the graph crosses the x-axis. And in fact, it should say x-intercepts because many functions have several x-intercepts. Also remember that we have several different names for x-intercepts. They are also called zeros, roots, or solutions. Usually when we get to pre-calculus, we simply stick to zeros or roots, but you may see any or all of them used. So let's look at the graph of 2x cubed minus 3x squared. So there it is. The x-intercepts can be estimated. They appear to be at 0 and 1.5. And 1.5 actually looks like a pretty good estimate for that. But what we're going to do is calculate them algebraically. So remember, x-intercepts are called zeros because they are where the output is 0. So f of x or y equals 0 at your x-intercepts. So we're going to plug 0 in for f of x, or for our output, and we are going to solve by simply factoring out the common factor x squared. We do that, we have x squared times 2x minus 3. Now we have two factors set equal to 0, and so like we've done since Algebra 1, we will set them equal to 0 and see that our zeros are in fact 0 and 3/2. All right, let's look at symmetry in graphs. We are going to look at the symmetry in the graphs of functions and relations. And I include relations because one type of symmetry we will look at will be for relations only, not functions. And you will see why when we go over it. There are three types of symmetry we're going to study. We have symmetric with the y-axis, symmetric with the origin, and symmetric with the x-axis. So let's get started. A graph is symmetric with the y-axis if and only if for every point xy there is a corresponding point negative xy, so a corresponding point on the other side of the y-axis. And we've seen these before. Look at y equals x squared. This is symmetric with the y-axis. The y-axis, in fact, is the axis of symmetry for this quadratic. Where we have the point 1, 1, we also have the point negative 1, 1. Where we have the point 2, 4, we also have the point negative 2, 4. So what this tells us is that if we replace x with negative x in this function, we will get the same equation. Think about this. Y equals x squared. That's really y equals positive x squared, right? If we replace the quantity x with the quantity negative x, the quantity negative x squared is negative 1 times 1x is just going to give you a positive x squared. This type of symmetry, remember, is line symmetry because it can be folded over the y-axis and remain unchanged. And this symmetry, symmetric with the y-axis, produces a specific type of function called an even function. And we will learn more about that a little bit later on. Now, a graph is symmetric with the x-axis if and only if for every point xy, there is a corresponding point x negative y. Now, looking at this graph, this is symmetric with the x-axis. And looking at it, you can see why. This is clearly not a function. This is a relation. The fact that for every point xy, so negative 4, 2, there's this corresponding x negative y, or negative 4, negative 2, the rule for this symmetry is also the reason it's not a function. So let's look at some points. We have negative 4, 2, and negative 4, negative 2. That right there proves this is not a function. For the input negative 4, we have two outputs, both 2 and negative 2. We also have the same thing happening at negative 1, 1 and negative 1, negative 1. So what this means is if we were to replace y with negative y, we would produce the same equation for something symmetric with the x-axis. Now, we don't use these a lot. This is line symmetry. It's folded over the x-axis, remains unchanged. We don't do too much with it. You may be asked, what type of symmetry does this graph have? And if it doesn't have y-axis symmetry or origin symmetry, you would test for this and say x-axis symmetry. But it won't be a function, so we don't see it all too often. A graph is symmetric with the origin if and only if for every point xy there is a corresponding point negative x, negative y. So the most common one we see here is y equals x cubed. So let's look at this. We have the point 1, 1 and negative 1, negative 1. So xy, negative x, negative y. What this tells us is that if we replace both x with negative x and y with negative x, y with negative y, we will get the same equation. All right, now this is not line symmetry. This clearly doesn't look like it's folded. This is point symmetry, as it can be rotated 180 degrees about the origin and remain unchanged. And it too has a specific name. Functions symmetric with the origin or symmetric about the origin are called odd functions. So we will work with both even and odd functions. And there will be many functions that are neither even nor odd. So we don't want to use a graph every single time we want to test for even or odd functions. So let's learn how to do it without a graph. Remember that we saw earlier, even functions are symmetric with the y-axis. Therefore, for every point xy, there's a corresponding point negative xy. So what does that mean? That means for f of x, if we put negative x in for f of x, we would get the same equation. Remember we talked about that. We said if we put negative x in for x, we would return the same equation. So we can do that algebraically and test for even functions. Is f of x equals 3x squared plus 1 even? Well, let's check. Let's see if we put negative x in for x, if we get the same equation we started with. So let's put negative x in everywhere we see an x. So negative x, the quantity negative x squared, is going to be positive x squared. So we are going to end up with 3x squared plus 1. This equation has remained unchanged even though we put negative x in, meaning 3x squared plus 1 is an even function. Let's look at f of x equals 2x to the 4th power plus x minus 4 and see if it is even. We'll do the same thing. We'll see if putting negative x in for x returns the same equation. So put negative x in everywhere we see an x. 2 times the quantity negative x to the 4th, well, that's going to be 2x to the 4th, just like we had here. Plus negative x, well, that's going to be a minus x, right? It's going to be 2x to the 4th minus x minus 4. That is what we get when we put negative x in, and they are not the same. What's different? The negative x was a positive x. So 2x to the 4th plus x minus 4 is not an even function. I'm going to give you a little trick. Not a lot of people teach it. I don't know why people don't like it. If you do this test enough times, this will become apparent to you. So we saw that 3x squared plus 1 is even, but 2x to the 4th plus x minus 4 is not even. And it's the x that messes it up, right? It was this x to the 1st power that messed it up. The constant was okay. Both equations had a constant, and this was even with a constant. But because we had a variable to an odd power, so we had a variable that was not to an even power, the function was not even. Giving us the rule that if f of x, so if a function contains only even powered variables, even if it has a constant, it is an even function. Let's do the same thing with odd functions. We saw earlier that odd functions are symmetric at the origin. Therefore, for every point xy, there was a corresponding point negative x, negative y. Remember we said that this means if we negate the whole function, negative y, if we put in negative y for y and negative x for x, we would get the same equation. So what that means is if we negate the entire equation, it will be the same as if we just negated the x values. Let's look at that. Is f of x equals 2x cubed plus 2x odd? Well, let's see if negative f of x, remember negative f of x just means we negate every term. Let's see if that equals f of negative x, where we simply negate all the x values. All right, let's first look at f of negative x because we're pretty familiar with it. So f of negative x, we put in a negative x for x cubed, and we put in a negative x for 2x. Well, negative to an odd power, this will be negative 2x cubed. Negative to an odd power, this will be minus 2x. So what we get is negative 2x cubed minus 2x. Clearly it's not the same as what we started with, but remember we're testing to see if f of negative x equals negative f of x. So let's negate the whole function now. Negative f of x means negate each term. So we're going to negate 2x cubed and 2x. We get negative 2x cubed plus a minus 2x. Let's clean this up. We know this doesn't make any sense. So we get negative f of x equals negative 2x cubed minus 2x. These in fact are the same, meaning 2x cubed plus 2x is an odd function. All right, is f of x equals x to the 5th plus x minus 1 odd? We'll do the same thing. We'll see if negative f of x equals f of negative x, right? We'll see if we negate it. We get the same thing as if we only negate the x. F of negative x means negative x, the quantity negative x to the fifth, plus negative x minus 1. That gives us negative x to the fifth minus x minus 1. Let's negate the whole thing. This means we negate every term. So negative x to the fifth minus x plus 1, right? If we negate a negative 1, that gives us a plus 1. So these are not the same. We've got a negative 1 there. We've got a plus 1 there. These are not odd. We have the same type of rule or trick, people would call it, for testing odd functions. If 2x cubed plus 2x is odd, but x to the fifth plus x minus 1 is not, it's because the constant negative 1 messes it up. We were okay until we got to the constant. So you can test this a few more times. Do the rule, test for f of negative x and negative f of x. But you will find that if the function f of x contains only odd powered variables and it doesn't have a constant, so no even exponents and no constant, it is an odd function. All right, what if you find you've done the test and it's not odd and it's not even? No worries. Most functions are neither odd nor even, so don't panic if both tests fail. All right, let's do a few questions. I know this lesson was a little long, but we can still do a few questions. Let's look at this graph, and let's ask, what's the domain of this function? All right, let's look at our x values. Assume we have arrows here, because my little Desmos graphing utility does not give me arrowhead options, but we've got arrows here. I'm telling you that they're there. So our domain is all real numbers. Remember, 1 is included in the domain. If you put in 1, you will get out 1/2, right? You will not get out 3. That's what the open circle there says. So what's the range of this function? Well, let's look at it. Lowest value, right here, 1/2. That's the lowest output. Here it goes 3 horizontally forever, but here, remember, it's going unbounded into infinity. So our range is 1/2 inclusive to infinity. All right. Let's look at one more page. Oh, I have a random box there. All right, let's look at which functions are even. All right, we have a few functions here. We have 9x to the fourth minus x squared plus 2. Let's think about what do we need for an even function? We need even powered exponents only, and a constant is fine. So let's see, we have an even power, constant's okay. That's even. Even power, constant, that's okay, that's even. Odd power, this is automatically not even. Even power, odd power, so this is not even. Odd power, constant, as soon as you had an odd power, it wasn't even. So let's look, which ones are even? There we go. Now, which ones are odd? So all odd powers, no constants. The only one I see is here, 5x cubed minus 4x. This one doesn't work because it has negative 4 there. This one doesn't work because it has a positive 4 as an exponent. So let's see what we get. Oh, look at there. There was a mysterious function there. My animation's a little messed up on this one. Let's check and make sure this is odd. Yep, we have an odd power 7, odd power 5, and odd power of 1. That is, in fact, an odd function. You could not have gotten that one right because it wasn't even showing, so good job if you did. And we have one more odd function. There we go. So what about these two guys? These are neithers. So we have odd power constant, so it cannot be odd. We have even power, odd power, so it can't be odd, can't be even. It's neither. Remember, if you are going through these lessons, you should be subscribed to our YouTube channel because you can submit any homework problems you get stuck on. There was a lot in this lesson. If you get stuck on something on domain or range or symmetry or even or odd functions, submit them to us and we will make you a custom video solution. Until next time, Math Hoppers, take it easy.